Please complete. Okay, welcome. This is a talk title taken directly or slightly abbreviated from the VR grant proposal I submitted a week or so ago, navigating the incomparable functional programming into multi-objective optimization. And well, the abstract is an abbreviated version of what was in there. So if you want to do decision making in high stake domains like climate impact research and fusion energy and so on, it's really very difficult or very expensive or even impossible sometimes to make trial and error experiments. So still, decisions require balancing different trade-offs. So we're talking about or proposing to do more formally verified functional programming, computer multi-objective optimization. And we had a paper on the understanding orders and functional programming in Pareto prompts and so on. So there's some slides from that and some from the grant application. This is joint work then with Nicola Botta from the Potsdam Institute of Climate Impact Research, Tunde Fulop from the physics department, and Tim Richter from the University of Potsdam. Okay, preliminary work. Well, what has been done from my point of view on this? So the most recent thing is the optimization under uncertainty preprint. So it's on archive, it's submitted to JSP. And just around January, February somewhere, we got the previous paper after like 3 years of struggling through reviews and so on published, which was about dimension analysis and coding up the pi theorem, which is sort of the theory behind dimensional analysis in dependent types. And we also had last year the paper with Jean-Philippe, which also took quite a while to get published, the domain-specific tensor languages paper. We've used both linear types and linear, in the sense of linear algebra tensors for some fun and profit. Well, maybe no profit, but maybe somebody can make profit from. Responsibility under uncertainty is slightly longer ago, to 2023. That's abbreviated here as matter most, because we had the subtitle, Which Climate Decisions Matter Most? And it was trying to apply our monadic theory of sequential decision problems from an earlier paper in some climate relevant case, where Nicola Botta was in an EU project, which has now ended, and they were doing some experiments and they wanted to sort of figure out what uncertainty meant for different decision problems. So if you're unsure about if your decisions will actually be carried out in the real world, that may change the optimal decisions to make. And even further back, I did a paper with Cesar in 2012 on dependent type programming and scientific computing, where we try to sort of argue that sometimes it's nice to have proofs and properties and not only tests and numerical stuff. And the inspiration for that, I think, was that when I talked to Cesar one day, he came and said, now I leafed through this entire book, and in his hand was numerical methods in C, looking for specifications. And I found 0 uses of the word specification. So, of course, they do specify things all the time. They say, okay, this is the algorithm, or this is some numeric problem we want to solve, and then we solve it. And then they say, this is the C code which solves it. Trust us. That's the way. But it wasn't really filled with tests and specifications and so on. So he said that, okay, scientific computing is in a bad state. We need to do increasingly correct scientific computing. So we submitted a grant proposal and never got funded. But there is a little bit of that trend. So hopefully, maybe this time, 13 years later, we might get something funded. There is a Pareto prompt there, but I will come back to it later, so I won't talk about it right now. But we want, like, as I said, build correct reconstruction software for multi-objective optimization. Okay, so the setting is simulation-driven research, and we have 2 application areas. One is climate impact research, where it's not just climate research, so it's not just simulating the Earth system, but it's also trying to involve humans and decision-making into it, which makes it, of course, much less certain. We focus on stylized problems. I'll get back to that on the next slide. And then the other application area is things with the plasma physics, fusion plasma. And there we've done a case study. We had some money from the energy area of advance at Chalmers. So we did a bit of writing there and research. So actually, I think my name is now on 3 physics papers as sort of one of the 6 co-authors or so. In both cases, it's some kind of function f from some input domain of controls, which I have to y for that, and x for the outputs, where we seek to minimize this f. I have to say, very often in physics, even if they have a multidimensional x, what they do in the end is they decide on a cost function, sometimes not even explicitly. They sort of take the average of the numbers or the weighted sum or some kind of measure, and then they get the real number, and then this send it into a Bayesian optimization algorithm. But I mean, the objective space is almost never totally ordered. So as soon as you pick a cost function, you've sort of decided on an ordering there, which may not be the right one. And then we'll talk a bit about that later. And then, of course, well, not always, but as I said, from the numerical recipes and so on, the model implementations are always never verified. So it would be fun to do something on that direction. So first, yes?
Yeah, so almost never verified. So are there specifications of the model that you could verify against?
So it depends by who you ask. If you ask the researchers doing this model, say, yeah, here's the research paper that we came from, and that has all the equations, and then we just implemented it. And then, of course, you, as a computer science, you ask, okay, well, how do you know if the implementation actually corresponds to the paper? And then they say, well, you know, within numerical accuracy and so on, but have you actually tried it? Well, we have some standard tests because we have this other group in the US who does it, and they have this Chinese group who does another way, and then we get roughly the same results, and then they're more or less happy. I mean, benchmarking is what they do. Benchmarking to other code when available or to experiments. It's a whole science in itself, because the models, of course, are never the real world. So it's always approximations. And then sometimes the approximation are pretty drastic. For example, my wife is now working on this project with space physics. And then they have the solar wind comes to Earth, and it sort of moves around in an interesting shape around the magnetic field. And then you want to track both the electrons and the ions. But the electrons are like 2,000 times lighter than the ions. So if you want to model both, you need sort of 2 completely different grids. So usually, but I don't know how they backport it, but often they say, okay, let's assume the quotient is just 50 and not 2,000. And that they can do stuff there, and then they sort of try to backport this to the real situation. That sounds like black magic, and I'm not sure if it actually works, but so sometimes these problems occur.
So if they have a bug in their implementation, it might actually make the stuff better than worse.
Yes, and I'm sure there are lots of examples of that, when they implemented something in the bad way, and then they got good results, and they publish it. And then they find out, like 2 years later, somebody tries to reproduce it, and they get confusing results, and if they're sufficiently eager, they might actually figure out what the bug was. I have 1 or 2 examples on my own there, but maybe we'll see if there's time for it later. So this was just one thing. We had to have in this Matter Most paper a little section about arguing why we do not use something very popular in climate impact research, which is called integrated assessment models. I think the simplest such that is famous is DICE, which was published by this Nobel Prize winner like 20 years ago, which is dynamics. I don't know exactly, it's just abbreviation. But there are lots of these models, and they have thousands of parameters, very big state spaces. And then there came a paper about misuse of models in 2017, where he used one of these standard models and tried to fiddle with the parameters to get the different outputs. And he managed. So he was arguing then, and we are sort of taking this up in one of the papers, that you can get a false sense of legitimacy if you have a big complicated model and you choose the parameters and then you get the result. And it's hard to know if you just pick the results that you wanted by tweaking the parameters, or if you're actually describing the world. There's also often too much determinism in these models. So they assume some average result will come out and then they compute with that. And what we try to look at are sort of what we call stylized models. So very low dimensional spaces, like having 8 states in the state space, or having a few real numbers describing the setting. And then yes.
What sort of parameters are you talking about? Are you talking about physical constants, or like how much salt is in the ocean at some place? Or
yeah, the physical constants are easier, but they're often economic things as well. So, for example, in this dice model, they haven't. I think it's like 50 or 80 parameters, and there are also things like how do we discount for future losses or gains? That's like one of the sort of main big parameters to be set at a rate of 5% or 10% or 2%, and you get very different results. It a little bit depends on how positive or negative you are about the future. But then lots of other things like, okay, do we assume that the technology will evolve at a certain rate? Or how do we handle, but I mean, in practice, they try to encompass uncertainty by saying that, okay, we make some factors here. So if we implement something which would have this effect, we will say, okay, it's 70% effective. It sounds like Pokemon. So there are, I haven't even read through the full list of those parameters. The DICE model, which is a simple model. So we did a little bit of sensitivity analysis in the fusion experiment, because also in the fusion experiment, they had this big code and they had lots of parameters and said, okay, let's just look at this without knowing. And there was a little Python script which ran this thing, and it counted 60 parameters, which were sort of set in different ways. And then we tried to run it with changing each parameter 10%. And in some cases, it would just crash if you change it 10%. And well, of course, because we did this naively, we just took all of them and without looking at them, and then some parameters were things like this should be 1 or 2 for which model for solving the equation of the ionization of something. And of course, in Python, it wouldn't complain that we put 1.1 as the net number of the model, but it would crash later, and so on. But so and some things were very sensitive, and most of the parameters did absolutely nothing. And probably that's because it's configuring parts of the simulation which is not really run in this ROM. Anyway, I should probably move on. So anyway, so explicit uncertainty is good to have. So you have to deal with either probabilities or perhaps intervals, so you know that the result will be in a range of parameters. And an interesting part there is that if you're unsure about the parameters, you may not need to be very, very detailed about your grids and so on, because there's so much uncertainty anyway. So, for example, in numerical recipes, they will have arguments about the order of correctness in the sense of what power of the step length is the error moving as. So is it proportional to the step length, or is it quadratic or cubic and so on? So if you get very small step length, how good will the precision of the result be? But that's about computing a result to say 10 degrees and 10 digits of accuracy. It's not really relevant if you know that the uncertainty is on a factor of 50% or 10% anyway. There's no point in having an asymptotically exact algorithm if you only have inputs or the model accuracy is only 10% anyway. So sometimes approximate computing is important. And I'm sure there's lots of research on how to do approximate computing well, but I haven't done the reading on that side. Anyway, we are hoping that if we do stylized alternative models, we can still learn stuff. We can say exactly what the result is, and then somebody will have to interpret them as the real world, which of course is the main jump there. Okay, formalizing is perhaps overdoing it, overword here, but we have some controls. A subset of all the controls are feasible, so we cannot implement not all if we have, so for example, a real number for a temperature, that temperature should not be negative Kelvin. So there are always some limits. And also, if you have an experiment, we may insert some gas into the fusion reactor, and we know how little and how much we can as minimum, maximum. So we have some intervals there. The objectives, the X space is the one we return in. It's often a tuple of real numbers. And within that, it's also we usually have a predicate which can check if the output is safe. Somebody's decided that the fusion reactor wall cannot withstand a force larger than this maximum force, and the current cannot go over 10 mega amperes or 1 kiloampere or something like that. And then we have a function, as I said, from y to x, and we try to find a collection of safe controls with some trade-off, because there usually is not just one which is best. And then, okay, what is this trade-off? This is just to illustrate. I think I might have used these slides at one other talk some other year. If we have a control space and objective space, this is a fake case. We're trying to get close to two different points in 2D space at the same time, which is impossible, so it's a trade-off. So here is an input space on the left, which is like reddish, and then on the right is just an empty grid. And it's illustrating the fact that we have a black box function. And black box here is not that we don't know the source code, because we often do. We have the simulator, the dream simulator for the fusion case, so we have the dice model and so on. It's just that it's not analytically tractable. We can't just look at the model and compute or sort of know the full behavior. So we have to actually run it to get an output. And running it means it takes some time. And for example, here we can run it at one point, little a, and then get some output. So here you can keep in your head the idea that this is supposed to minimize cost and temperature raise for a climate case. So this apparently has 3.5 on both in some units. And if we only evaluate this one point, of course, we know very little about this red rectangle. So let's pick another point. Okay, this is nice. This is now, let's see if I can get my cursor. So this B has a lower cost, a much lower cost, and also a slightly lower temperature raise. So clearly B is preferable to A. And also this happens to be another point which is preferable to A, but we cannot a priori tell if B or C is best. So that depends. The policymaker is more interested in reducing cost, in which case this is better. This has just one unit of cost, or reducing the temperature raise, in which case this would be better, even though the cost is higher. And if we continue evaluating a few not very random points, then you see this point in the middle here ends up actually closest to the origin, and distance to the origin and this output space could be one of these cost functions I mentioned earlier. So if you think that distance in the Euclidean sense in this coordinate system happens to be the right trade-off, then this is actually the best point, E. But of course, you don't know if this temperature raise and this cost, what they are measured in, if this is billions of dollars and this is micro Kelvin or something like that, then it doesn't really. It matters really what the units are. Yes.
So I'm trying to understand. So your point is this is this Pareto thing, right?
Yeah.
And but you don't know what the policymakers are going to want while you're doing this analysis.
No.
But why is that? Because if you know the cost of billions of dollars
usually-
and the other is microkelvin, then you don't care.
Yeah. Well, so okay. So the units are probably known, at least to this case, but the trade-off between them might not. And more importantly, different people will have different opinions. So the Green Party and the car driving party may have.
You want to do one analysis.
Yeah, but.
Or and then where all of these policies later on, they can ask questions and they can.
Yes, so in practice, you would have some kind of iterative thing. So for example, if maybe at this stage, you're happy. You got these 5 points, you present the results and say, what do you prefer? And clearly, I mean, if we move to here, B, E, and C. So this happens to be a case where I have the formula, so I can compute for infinitely many points where it would end up. And the grid on the left becomes this sort of folded up bag here. You can see that you can get close to the origin, but there is a trade-off. And perhaps you would like to report that B, E, and C are sort of interesting points. And then the policymaker might say, well, actually, I'm interested in something between B and E, close to B. And then you would probably run a few more runs zooming in towards that direction. So it would be nice to have well, it doesn't need to be lazy, but what do you call it? Iterative, I mean, a stepwise refinement, so that at any point you do more, because it takes some time to do these runs, so you don't want to necessarily compute everything beforehand. I mean, traditionally, what policymakers would do, they would send it to a consultancy company, who would wait 3 months, and they would get a report back. Then they read the report, it has 3 scenarios, A, C, and D, or whatever, and then they pick, or they try to approximate between them somewhere. And hopefully, if you have a reasonably reusable system, then you could perhaps be a little more interactive there and do some experiments. That's the hope. I wanted to say, yeah, that you want to compute and present points on or near the Pareto front. I mean, strictly speaking, mathematically, the Pareto front is really unattainable unless you sort of submit all the real numbers and then you get the exact Pareto front as the output, but that would take infinite time. So in practice, you get an approximation. And unfortunately, you don't really know how close you are to the real thing either. Because if you have just a few point evaluations, there might be hiding somewhere in the input space a region which is much better. For example, if you think about looking for the lowest point in the new normal landscape, and then there is like, okay, it's mostly flat, but somebody's drilled a well. So it's like 20 meters deeper in a little circle of this size. And before you find that, you will not know that it exists. On the other hand, if the purpose is to land a helicopter at the lowest possible point, you're probably not interested in this size well. So you might also be arguing that if you cover the space to a certain granularity, you're done. So there are some measures there for progress. There are some challenges as well. When you start thinking about multi-objective optimization, then people are very creative. And they come up with lots of objectives that would like to compute, sometimes infinitely many. And clearly, a multi-dimensional optimization with infinitely many outputs, the Pareto front will be very complicated. Because here, the Pareto front has 1 dimension less than the space, so it's a 2D space and it's a curve. If it would be a 3D space, it would be a surface. If it would be an n-dimensional space, it would be an n-1 dimensional manifold. And with a few evaluations, finding the shape of that is going to be difficult. So hopefully you will have to keep your dimensions rather low. Anyway, there was a case study, as I mentioned. We did two years of work together with the physics group. They developed a computer-based framework for simulating. There was a PhD student who's now an assistant professor in Stockholm, Matthias Hoppe, and he developed the DREAM simulator. Disruption, runaway, electron analysis model. They like these abbreviations. They also have a code called GO, G-O, and another code called CODE, C-O-D-E. They managed to find abbreviations. They're completely ungoogleable. Anyway, this one is called DREAM, and it specifically computes something about runaway electrons, the details for when needed come later. But in simple terms, it's a function. You put in some parameters, you get a run out, and that's the outcome of the experiment. This is the result of such a case study. Let's put this slide up. I will zoom in soon, but first saying that on the right of the 3 squares, there's a Pareto front, and that's showing some trade-off then between the runaway current, something you want to keep low. Actually, here it's the 10 logarithm of the quotient of the runaway current with 1 megampere or something like that. So you want it to be small currents, and -3 I think means, no, it was 10 megaamperes. So -3 I think means 10k amperes. So lots of current from a household perspective, but much smaller than what they started with. And what they do, the two axes, so this is the output space, this is like X, and this is two views of the Y space. So one is drawing, it's a contour plot, or rather, a color plot of one of the terms which should be minimized, and the other term which should be minimized. Both should be in the very blue end. So you don't want to be here in the red part, and you don't want to be there in the red part. So this is some of the trade-off, because it seems like this corner is bad here and this end is bad there, so you want to be somewhere in between. And you could zoom in more as well. And actually, I will do one zoom here, which is to explain a little bit more about how we got here. Zoom. Yes. So all the gray dots here are runs of the model for this particular case. I think it was 400 runs, something like that. So, and
How long is one run?
Hmm?
How long does one run take?
Here it took like 4 minutes per run.
Okay.
So 400 times 4 was overnight.
So they were decided on beforehand which runs you were going to do? Or
No, this was based in optimization.
Okay.
Well, actually, no, this was not based in optimization. This was adaptive mesh refinement. So we started with a rectangle in the input space. We ran the 4 corners. And then we have an estimate for the uncertainty, which from the first run is then huge. Like it could be anything from minus to plus everything. And then we split it into 4 quadrants. So it's a quad tree. And then we compute the middle points for these, and then we sort of continue inwards where things seem to be promising. So here you can see a bit of the result of that. So this is the input space. So each black dot is a run. And you see they get very close together here near the Pareto fronts. So it tries to be guided by filling in the Pareto fronts. But I mean, first run, maybe that was this point. And then the second might have been that one, which would then disqualify this because this is clearly better. And then sort of step by step, it sort of creeps on down towards the origin. We also experiment a bit with the visualization. So here it colors the points on the Pareto front from one side to the other. And it's just 2 things, which means the yellow things will be the best in one of the parameters and the worst in the other parameter out of the optimal ones. So you can sort of rank them in the 2 directions. And then this is because you want to see where they are in the input space. But apparently you first move upwards like that, and then you go down, and then suddenly you jump here, and then you move a bit, and then you jump here. So there is no guarantee that there'll be anything continuous when you do this sort of inverse image of this. There might be scattered islands. If you have some base function which is almost flat, and then it's like you add sine 5x plus sine 10y or something, so you get little bumps everywhere, then every little bump will be sort of near the optimum, and you will get a lot of scattered points. Anyway, so what I wanted to show here is that we've actually done some runs and tried to understand it. I can't argue that we have any verification of the correctness of these runs, but at least the Haskell code, which calls the Python script, which calls the C++ engine, we have a bit of control.
So the input space has 2 dimensions, and the output space also has 2 dimensions, or
yes, in this case, actually, yeah. So it's simplified because the output space had 4 dimensions, but these were the 2 most important ones. So you also, when you do a number of these runs, you get a bit of the geography of the 4-dimensional space, and then you can see, oh, okay, some of them doesn't really matter.
And then each output also has an uncertainty.
Well, they should have an uncertainty, but they don't.
Okay.
So I wanted to dig into that, but we never got to it in this 2-year project because, I mean, for example, you can do sensitivity analysis by wiggling the input parameters, and there are also 3 modes you can run Dream in. So we want to have this tower of simulators where the sort of the fastest one, the 4-minute one, is the sort of approximate thing, and then there's one which takes 4 hours, which is more precise, and then there is one which takes days per point, and then you could sort of here and there, in some cases, run the more detailed.
You could do automatic differentiation instead of quickly.
Well, we could if we had the whole C++ code using dual numbers.
It's been done.
It's been done, yes, but if not for this code, but yes, that would also be very fun to do, to see. I mean, basically, as in Haskell speaks, to replace the real numbers by another type class instance to get it to automatically do the derivatives. But no, it doesn't. And it's partly because it's several things inside. So because it's using a few solvers for the different time steps and so on. I mean, it actually keeps track of about 100 different atoms plus ionization states. And then it has an electromagnetic field, and it does this in a phase space. So there's both velocity dimension and space dimension. So there's lots of garbage in there. They worked years on this.
Well, I mean, it's totally doable, this thing with doing AD on C++. Many banks do it for their whole Monte Carlo models are turned into something that can be.
Yeah, I mean, if you have resources and research engineers to actually rewrite their codes, then that would be. I haven't.
No, I mean it's work. Yes.
Yes. In the research setting, I'd be happy to get a funding for one PhD student as a start point, and then maybe you shouldn't all be doing rewriting of the code. But yes, definitely, the technology exists to do more fun stuff here, and in several directions. Okay, now to something. The underlying theory is something that the paper talks a bit about, because this most recent paper is not really about any fusion. It's just about this computing the operator front and so on. So just to go back to more of Kuhn's discrete math course and stuff. I'm not sure if pre-orders are in there, but anyway, it could be. So just to remind people, we have pre-orders. That's a relation which is reflex state intransitive. For example, if you compare strings by their length, so cat and dog are equally long, but they're not equal strings, but they are less than equal to each other. So it's an example of a pre-order. Partial order is when you add anti-symmetry, which disallows this cat and dog example, because if you have two things which are less than equal to each other, they must be equal. And then the subset relation is a typical example. And then you don't have, I mean, then if X is subset of Y and Y is a subset of X, then they are actually equal, but you still have things which are incomparable. So for example, the units, the singleton subset 1 and 2, they are just not less than equal to each other in either direction. And then of course, the thing we usually think about mostly when it comes to orders is the total order, when you add the totality requirement, which means that either for every pair xy, either x is less than equal to y, or y is less than equal to x. So in one of the direction holds. And then you can line all the numbers up in a nice line and so on. And that would guarantee a single unique minimum. But why do we don't have that in the operator front? Well, you take two relations, you make a product relation. In this case, you take two orders and you order them component-wise. So a pair is less than equal to another pair if the components are less than equal. And that of course means that 1, 1 is smaller or equal to 2, 2, but 1, 2 and 2, 1 are now incomparable. And that's the typical case. I mean, the loss of life and economy and loss of money and so on could be two different dimensions, and you don't a priori have a price on a human life, and maybe you don't want, for ethical reasons, to even put it in your report. So then you report the two numbers together, and then you have this partial setting. So totality lost, and that's why you need operator fronts. You have incomparable elements, multiple distinct optimal compromises. And to illustrate it, zooming in on the example, and a climate example, then this is like 7 possible points here. Oh, I should say first, very often when you look up operator fronts, they talk about dominance, the dominance relation. So the dominance relation is usually written with a little curved less than sign, and it's the strict version of the less than equal in the product order usually. So no component is worse. Also X is strictly better in one component and less than equal in the other. So, for example, I think here P1 here is better than Q3 because even though it has the same X2 axis, component, it has a much smaller x1 component. And the illustration here, the little red things, I think they're called cones in the literature on multi-objective optimization. So every point has a cone, which is like everything above it, which is worse. So every point here, P1, P2, P3, P4, dominates everything in this sort of reddish place. So if you have these 7 points, then you would throw away the Qs because they are all dominated by one or the other of these points, and you would keep all those 4 points. And if you would, let's say, if you would get a new point here, maybe I need to squiggle a bit. A new point here, that will be added to the Pareto front. It would be a new point there. If you would get a new point here, it would dominate P2. So P1, this new point, P3, P4 would be there. And if you would manage to get down to the origin here, then all of these 4 points would be suddenly collapsing into a singleton Pareto front, which would dominate everything else here. Anyway, mathematically, the Pareto front is just a set of minimal elements under this order. So it's not just one element, because you have this incomparable elements. And yeah, that's why the Pareto front is relevant. And there is a bit of a challenge when you look these things up. So the Pareto front, usually in math books, is computed assuming the input is like all real numbers in the space and so on. And we really want to work on actual finite sets of points, because that's what you would ever get from one of these evaluations runs and so on. You collect a number of points, but never more than finitely many. So you will have to actually have the Pareto front with relation to the points that you've got. So any set of points of outputs, you can compute the Pareto front of. It's just a discrete operation. And this is the operation that's not very surprising. If you have a list of points, a finite list of points, you can bump one point into the list once at a time. You assume that you have already computed the Pareto front for the rest. So if that's nothing, then you get the point. If it has 1 point and some other points, then you compare the 3 cases. If it's one is dominating the other or the opposite, or neither is dominating each other. So let's take that slightly more detailed. So if the new x is equal to the point already in the front, there's no point adding it. And also, if the first point on the front dominates this x, also there's no point in bothering with the x. The x will be above, it will be covered, and we just ignore it. If x dominates p, then p is no point in keeping. So we keep x and we will remove. So this is basically filter not. We will remove everything where x dominates from ps. So it might throw out some new points as well. And otherwise, this is the case where p and x are incomparable. Then we have to keep p because we don't know if p and x are best. And then we have to see, does x fare well with the rest of the list? Because it might be that the rest of the list will dominate x and then it will throw. Otherwise, it will end up being added to the list. Yeah, the details are not that important. And now, as I should finish in time, this is just to know what I applied for. I said we want to combine functional programming, dependent types, dimensional analysis, and so on, and make some interesting stuff. First work package is verified specifications and order theory. This is the part I haven't talked about in these slides, that what happens when you output not even a tuple, but actually a probability distribution or something like that, or a set. Then work package 2, try to reduce the stirred space because it tends to be too big. And then sometimes you can use dimensional analysis, which is sort of parametricity, but for physics. And during simulation, you can do things like this adaptive mesh refinement. You can sometimes exploit symmetries. You can use deterministic systems. You can know that you don't have to run it again. And sometimes it's approximate computing. If you know that something about the derivatives, you know that you don't have to go further into a certain region because it cannot vary more than a certain amount in there. And finally, we have these 2 case studies. We want to do some examples on the climate side and some examples on the fusion side. And the interesting detail here, perhaps, that there was a recent paper, it's on arXiv still, about let's see, I have to click on this to make sure that I get the title right. Bounded error, algebraically composable neural solvers of partial differential equations. So this happened to be a top speaker at the seminar at the physics department about fusion, because he applied it to fusion, but they made a domain-specific language embedded in bracket, which generates the C code for the solver, and they say proves the IEEE 700, so the approximation bounds. So it says if you have inputs within an epsilon, the output will be within L epsilon, where they compute this L. So they compute how much it can sort of degenerate the approximation. And when they say prove, they have sort of hand implement something in this bracket thingy. So it's not that they prove with Agda or Lean or so, it's they're sort of doing algebraic manipulations and they say, this is a certificate. So it's worth looking deeper into it, and I haven't had time to do it yet, but it's the fun stuff here is that's actually, I could argue that we're using DSLs for something with physics, and somebody else did it, not only me. Let's see, I should be back to that slide. And then, summary conclusions. Multi-object optimization is fun stuff when you have several outcomes you want to minimize simultaneously. And ongoing work, there's a bachelor student who tries to write on doing this computation in parallel. If you have a big set of points, split it up into 2, compute Pareto forms of the 2 and merge them together. How is this algebraically and efficiently done? And then, as I mentioned, this functorial uncertainty, when you have probability distributions or sets of outputs, how should you then do with the relations, and how do you actually even specify the correctness? So the reason I'm saying even specify it sometimes, so this last point here is something we, let's see, I should be back to this one. Sometimes it turns out that disagreement about simulations and so on is not necessarily from different outputs, but different interpretations. So you compute, say, a probability distribution or a few scenarios. And some people will say, okay, we take the expected value. We have probabilities, we compute the expected value. That is the outcome. That's what we optimize for. And other people will say, well, we have to be very careful. Let's optimize to keep down the maximum, so the maximum possible harm. And then, not surprisingly, you get completely different results if you try to minimize the maximum or minimize the expected value. So there's this example like, okay, the average depth of the river that I'm going to cross is only 1 meter, so I can cross it safely. But it's actually 10 centimeters everywhere, except 3 meters in the middle where it's 10 meters deep. So the sort of expected value or the average may not always be the right measure. Anyway, and we want to look at designing DSLs, uncertainty, and so on, and find out to try to get a little more, as I said, increasingly correct scientific view. So, thanks. Questions? Yeah.
So how is this related to Bayesian optimization? Because there's also Bayesian optimization methods for multiple objective.
Well, we try to use Bayesian optimization in this physics project, and that's what they used mostly. And we were just a little bit annoyed by the fact that this was yet another black box. The actual Python library for Bayesian optimization, it did stuff and it gave a result. And there are sort of assumptions there, for example, about the smoothness and the correlation between different possible outputs. And so, for example, we ran it on one of these cases. We said, okay, the minimum sort of current, this runaway current you could get is 1 mega ampere. Okay, how sad, but maybe that's the minimum we can get to. But then Nicola said, okay, let's try to run this rectangle that I showed, this sort of red rectangle. Let's make that small, thin rectangle around the optimum it found, and then run it again. So we ran it again and said, oh no, the minimum is 200 kiloamperes. So a fifth of the previous run. And then he made a rectangle in the other direction of that, and then it was like 50 kiloamperes. So like by that it was 40 times better than the previous minimum. So the reason we started with this adaptive mesh refinement and trying to get error bounds is because we felt that the most, theoretically probably the most efficient way is to do this Bayesian optimization. You take one point at a time and you learn a surrogate model of the function, and then you sort of try to evaluate the right points. But it really, it really requires you to have the right parameters there again, because this, I mean, like, if you read the fine print in one paper about Bayesian optimization, it will say, well, we have this model of the correlations of the different functions and so on, and this is our model. It's usually, it's like one out of three, which is more popular there. And then if you pick the wrong one, you get different results. I mean, you could say wrong results. I mean, the minimum is always a value that you get from the result, but there might be a minimum which is half as big. So, we were not very happy with the results of blindly applying Bayesian optimization. But if you cleverly apply it, you can probably do good. I'm not sure if that was enough.
Okay.
Yes.
So what is now eventually sort of you said something about formalization, and is there eventually a proof that something is optimal with some respect, or what is the output of?
Yeah, I mean, if you specify a problem and you compute something, you want to know that the result is within a certain bound, for example, of the true minimum. So say that you can, if and then you have to assume things. I mean, if you allow, this is real numbers usually. So if you allow the input function to be any function, for example, the function which is 1 on rationals and 0 on the rest, then good luck for having any result, because then you will have to evaluate it for real numbers. But if you have a bound, a smoothness bound, if you know that this partial derivatives is maximum this and that, then you can give guarantees, but it's always sort of conditional guarantees. So if this holds, this will hold.
And the black boxes that you work with, these models come with these bounds?
No. And usually they don't even come with a specification of the right inputs, which is sometimes a bit annoying. Maybe I should let Niklas set up, but but I just want to check if when we're supposed to position. No, so I haven't done these beacons or the detail in this beacons work where they actually prove bounds in the sense of if you have an epsilon error here, it will not multiply more than L times epsilon that you compute this L. And then it's, it looked like the kind of thing would be fun to do.
I see. It would be nice if you sort of like can give some sort of requirements for the black boxes. Sort of that there's like a modular thing where they can say, okay, if you can guarantee me this, I can guarantee you this.
Yeah. I think there's lots of things to be done when it comes to scientific software and preconditions and internal invariants and so on. Because, for example, there was a problem 2 years ago when some problem was, so the dream simulator sometimes crashed. And then somebody was annoyed, a math student was annoyed because his case is it crashed like 70% of the points it crashed, and he couldn't figure out why. And then they tried to sort of dig down, and he found a place where they computed the sort of how many ions of different kinds are there at a certain temperature. And the temperature that was computed by another module ended up being negative kelvins. And then the model they had for the abundance of different ion species completely went berserk, not surprisingly. I mean, you assume usually Kelvin temperatures are positive. So clearly, any reasonable person would have a check somewhere that the Kelvin temperature output of this function may never be below 0. It's just unphysical. And I think there are lots of low-hanging fruit on that side. So that could be another project, just looking over numerical codes, inserting even just preconditions and invariants, I think would catch lots of stuff.
Types, maybe.
Oh, maybe types. Yeah, I didn't say types here because I think the story for positive numbers as a type in Haskell, for example, or like that, it's not very pretty.
No.
So I think preconditions and properties and so on, we have to be a little bit flexible there on what exactly is types and what is checked runtime or proven. Pragmatically, that's what I mean. Okay.